ressources.
Okay, great. Thank you very much, Laura. Yeah, it's my pleasure to introduce Professor Berend van Wachem, who will be lecturing on gas-solid flow today. Berend is an alumnus from Delft. He did do a master in physics and his PhD in let's say the predecessor of the chemical engineering department. Actually in the same group as I did do my PhD, so we know each other from that time. But Berend has been traveling quite a bit since then. After his PhD in Delft, he took up an appointment in Eindhoven, then moved to Sweden in Chalmers. After that, he went to London, Imperial College, where he was first lecturer, then professor, and most recently he moved to Germany, where he is now chair in the process engineering group at the University Otto-von-Guericke in Magdeburg. And well, Berend has been doing a lot of modeling of multiphase flow. He's really an expert in computational fluid dynamics, particle type simulations. And today he will be lecturing on modeling of gas-solid flow and how to do this with a two-way coupling when you have to deal with particles of different sizes. So Berend, we're looking forward to your talk. The floor is yours.
So thank you very much, Ruud, for the nice introduction. So before we start, so about 3 years ago, I moved from London to Magdeburg, which is a medium city in the east of Germany, working at a Department of Chemical Engineering, you could say, and I'm the head of mechanical process engineering. So there are 8 chairs at chemical engineering, and I do everything with process engineering, which is a lot of multi-phase flow work. So I'll give you a very short introduction what we do first in my talk, and then I'll look at 2 frameworks to model particles and flows. The first one being a fully resolved methodology, and the second one being Lagrangian particle tracking, and I'll compare the two. And for the second part of my talk, I'll focus on this Lagrangian particle tracking technique and try to identify what is the error in using Lagrangian particle tracking to describe a flow. And for that, I will look at what is called the undisturbed velocity, and I'll explain what that is when we come there. The last part, I'll look at how do we correct the errors. So the errors we make in Lagrangian particle tracking, is there a way that we can correct the errors to actually make Lagrangian particle tracking close to a fully resolved type of flow simulation model with a similar type of accuracy. So that's our holy grail, you could say, in the end where we want to move towards. And I'll finish my talk shortly with some brief conclusions. So first of all, what we do in mechanical process engineering. So when I came here, there was nobody really. And at the moment, we are now looking at 13 PhD students who work on a variety of topics, ranging from particle technology, so making particles, nanoparticles. We do a lot of things with complicated shapes of particles in flows, but also in heat transfer. We look at how do we measure specific particles, so how do we measure adhesion force of a particle. My own background is in multi-phase flow, so dynamics of particles, particle turbulence interactions, also a lot of things with film flows and surface tension, and recently we've also started looking at 3-phase systems. And finally, we do a lot of numerical method development, so almost all the simulations we do are with our own tools that we've developed over the past 20 years or so, ranging from discrete particle modeling to Euler-Euler or fully resolved gas particle flows. So that gives you kind of an idea what we do. We are, for a large extent, looking at fundamental research, but we also look at applications, obviously. Many are in nature and industry, such as sediment transport. So you look at the sand here, transported with a turbulent flow, in this case, a big river going into the sea. We look at things as sprays, as can we predict or can we measure what kind of droplet size we get from a atomizing spray. We also look at the effect of chemical reactions when we look at biomass combustion, for instance. and all kinds of processes with particles, from coating, drying, granulating, breaking particles, which is of course very important in also many process industries. So my talk today will focus on particulate flow modeling. And in a nutshell, there are three ways that you could model a particulate flow. So in this case, the black boxes indicate the resolution of the fluid flow. So you could say in CFD, it's the size of the mesh. And here all the way on the left, H throughout my talk will indicate the size of the mesh. We have a very small mesh spacing, in fact, much smaller than the individual particles. And if we resolve the particles in that way, we call that a fully resolved simulation, which has really taken off in the last 10 years or so. So we see many talks nowadays on fully resolved simulations, even in cases that they're not really fully resolved. And I'll address that in just a bit. In the middle picture, you can see that the fluid phase is resolved on a scale which is bigger than the particle, but not much bigger, typically between 4 to 10 times bigger than an individual particle. And we call that an Euler-Lagrange modeling framework, or Lagrangian particle tracking. And one of the things of today's talk will be to focus on that, to see what kind of errors do we make in comparison with a fully resolved approach. That's the first part. And the second part is, can we account for those errors so that we get an accuracy which is similar? All the way on the right, what I call an Euler-Euler is that we have very large mesh shells which are significantly larger than individual particles. In this case, we typically also don't track individual particles, but we solve a stochastic equations for the behavior of particles and for the fluid. So we have typically a RANS, Reynolds average number, Stokes approximation for the fluid, and a kinetic theory or a population balance model for the particulate phase, where we're not so much interested in the behavior of each individual particle, but what is the probability of finding a particle with a specific size and a specific velocity at a given point. I won't talk much about the third scale, but I'll focus predominantly on the first two. So to start with, I'm going to talk about this fully resolved scale, so that we have a mesh refinement where we resolve our fluid on, which is significantly finer than the individual particles. So what we do in this case is we have two levels of representation. The first is our Eulerian. So that's, we can see here our mesh, where the X denotes where we solve for the fluid velocity and pressure. And we have our immersed boundary, as you can see here, where we have these black dots are what I would call markers, where we enforce the no-slip condition between the particle and the fluid. So we have an Eulerian flow domain, and we have a Lagrangian or a moving immersed boundary, IB, where we enforce the no-slip condition between the two phases. So in a cell here, we solve the discretized version of our Navier-Stokes equation. So for short, we say that the change in velocity of the fluid, which is u, plus the convective terms, equals the buoyancy pressure terms, diffusion terms, and the forces working on that fluid cell. So that we basically do a standard single phase CFD type of discretization. And what we do near each of the markers is we say that we are interpolating the fluid velocity to our marker J in this case. So we have an interpolation step to account for the fluid velocities, and we get a value of the Lagrangian velocity, so that's capital J. And what we do is we compute a source term at point J to account for the no-slip condition, so that the fluid velocity and the particle velocity at point J have exactly the same velocity. And once we have the source term at our Lagrangian point or a Lagrangian marker J, we spread out this source term again, that's our small gamma here, with the same spreading operator to the Eulerian mesh, and we apply that. So we have some kind of smoothing weighting functions, we have some Eulerian cell volumes, and we have some Lagrangian marker volumes, which you need to find closures for, you could say. And if we do that right, we get a fully no-slip condition along the surface of the particle, at least specifically in the marker points that we indicate on the particle. So we've done many simulations over the years. So this is just an experiment which I'll come back to, which I did during my PhD in Delft, actually. It's a very small fluidized bed, which we did to actually look at the accuracy of Euler-Lagrange particle tracking simulations with a I think U of about 1.2 times UMF. We are resolving the particles with slightly over 6 mesh shells per diameter, and we have a compute for the collisions between the particles with a DEM model. And what we find is that we get a reasonable prediction of what happens in the fluidized bed with that, although we also realize that the resolution of 6.2 is far too small to really get a very accurate simulation of such a fluidized bed. Although this simulation is already extremely expensive. It already takes a week on a large supercomputer to compute a couple of seconds of real time of such a fluidized bed. So these fully resolved methods are extremely expensive. They have a potential to be accurate, but they're also very expensive, and they require a very, very high resolution. So there are many papers out there which say that they do fully resolved methods, but I would say if they resolve the mesh with less than about 30 to 40 cells per particle diameter, it's very difficult to claim that it's a very accurate, fully resolved simulation. So in practice, what you need is an adaptive mesh, as you can see here on the left, which we're actually currently under development. So where you have a particle in flow and you resolve the mesh adaptively as the flow develops. That means you save mesh shells in areas which are not very complicated to model, but you can include mesh shells where they are needed, namely at the particle where you are enforcing the sources for the no-slip condition, as well as away from the particle where you have very complicated flow features or features of the domain. For most practical cases, this fully resolved methodology is not feasible, and it won't be in the coming 10 years either. If you look at the number of particles in a fluidized bed, there are just far too many to be able to capture with such fully resolved methods. In the Euler-Lagrange, we typically still account for, or solve for the individual particle position, but we solve the gas phase at a much coarser scale, and we apply some empiricism to account for the coupling between the particles and the gas phase to couple the two. And this is a much more affordable way of dealing with a gas particle flow. In fact, we could do simulations with a few 100 million particles for the cost of a fully resolved simulation of maybe just a few 100 particles. So I would say with the current computational power, the Euler-Lagrange method is really starting to move in towards the realm of being interesting for applications. So what do we do in an Euler-Lagrange particle solver? We solve the fluid flow equations, and the fluid flow equations are given by the Navier-Stokes equations. So here we have our continuity equation on the top. Here we have our momentum equation, so the acceleration of the time, convection, the pressure term, diffusive terms, and the momentum exchange term with the particles, m. And together with that, we solve the equations of motion for our Lagrangian particles. So this is really just Newton's second law. The mass of the particle times the acceleration of the particle equals the sum of the forces, which includes the fluid force and the body forces. And if you look at the seminal works of Maxey Riley and also of the Gatignol, we can say that these are drag. So I've written here the Stokes drag times the correction factor for the particle Reynolds number times the flow velocity minus the particle velocity is plus the pressure term plus the added mass form and the history. And what we do then locally is we compute the forces on the particle, and we gather the particle forces in each fluid cell, and that becomes our momentum exchange term, which goes back into our fluid above here. So that looks like a pretty solid framework. It was first proposed by Crow in 1977, and it's used enormous nowadays. So any commercial flow solver will have such a model incorporated. So talking about the errors today, what is the problem with this framework? The problem is that in this term here, we don't need to insert the actual fluid velocity. What we need is the undisturbed fluid velocity at particle P. Or in other words, the velocity of the fluid if that particle were not there. Yeah, so we take out the particle of the flow. What would the fluid velocity have been? And then we can estimate the drag. And that's, of course, a big problem. So what we could do is we could run two CFD simulations, one without that particle and one with a particle, but that would be very complicated. So how do we resolve the fact that we need to have the undisturbed flow velocity rather than the actual flow velocity which we are computing for? Typically what is done in the literature, and I know that every commercial code does this, is they say that the undisturbed fluid velocity given by a wiggle over U, they take that to be the same as the resolved velocity. So they just, when computing the drag, they say, well, the disturbance will be small. We're just going to take the same velocity as we get from our CFD solver to compute the drag. So in the first part of this talk, what I'm going to do is I'm going to define the error, and the error in that really is our UF prime, which is the magnitude of the velocity disturbance induced by the single particle in our flow, which is the actual velocity that we get from our CFD simulation, so the actual flow velocity if we have the particle in, minus the undisturbed flow velocity. Now what we can already sense, of course, so a gut feeling, is that the magnitude of this self-induced disturbance will increase as we start making the mesh finer. Because if you have a very fine mesh, the particle that we're resolving is going to have a very big impact on the cell or the cells that it occupies. So we already have a gut feeling that error is going to scale as dp over h, where dp is the diameter of the particle and h is the mesh spacing of our fluid mesh. And that's why already Crow in 1977 realized we can only do this if the mesh we were resolving on is much larger than the particles, or that the particles are much smaller than the mesh spacing. So dp has to be much smaller than h. And over the years, I've given many seminars on best practice guidelines for multi-phase flow computations. And we've always said, well, dp over h should be in the range of 5 to 10, without really knowing what the error is. And our work that we've been doing really is, can we identify the error that we get if we are using UF at P being the same for the disturbed one as the undisturbed one. So basically saying that UF at P prime is 0, as is done in most commercial and academic codes at the moment. So the question is, how large is the error that we're making? And for that, we're going to try to estimate what UF prime is. So I'm going to confine myself to gas-solid flow so that we can say that rho P is much larger than UF. So the forces on the fluid are just a drag. We don't have history forces or added mass forces, which would make the analysis a bit more complicated. And I'm also going to, for the first part, look at the dilute regime. So I'm not going to look at the collisions of particles, which would also make things more complicated. So if we just substitute the fluid velocity as our disturbance of our particle plus the undisturbed flow in the Navier-Stokes equations, we get equations which are very similar. In fact, they're the same as you would get with a Rans type of model, where we now have an equation expressed in the disturbed velocity. So this is the velocity disturbance caused by the particle as it evaluates over time with the usual terms. But now here we have on the right-hand side the drag term of that particle with a Dirac delta function, because we only have drag where we have the particle. So only if this Dirac delta kicks in, we have the drag at that point. The Dirac delta in the work of Crow and in 1977 is just that we get 1 over the cell volume if the particle's in the cell, and it's 0 elsewhere. And that's why we call it PSIC model, which stands for the particle source in cell model. So the sources seen by the fluid are just accounted for by the cells in which the particle is located. And this is in fact the model standard used in literature. Can we solve that? Well, the Navier-Stokes equations are very difficult to solve. So what we can do is, as a first step, we can say, well, if the Reynolds number is very small, so we can actually neglect the nonlinear term of the left-hand side. So we're now solving our equation where we have a UF bar only. So we are actually overestimating the effect of the advection term. And then we can make an approximation of the Navier-Stokes equations. And we can look at two effects. So we can have a particle standing still. So Vp is 0, and we have a fluid velocity from the far stream, which I'm going to denote as U infinity. which is exactly mathematically the same problem as a quiescent fluid through which a particle moves with a terminal velocity of minus u infinity. So if we have our particle here in this sketch, located at xp, we're interested in the fluid disturbance of that particle at a distance r away, where we have the distance in point x given by an x coordinate and a y coordinate. And we're going to try to find a solution to this equation. And in fact, I first came across this in my Burgercentrum course, Advanced Fluid Mechanics, the Oseen approximation. I hope the course is still given. And for the Oseen approximation, we can actually find an expression, which is actually quite a complicated expression. And I don't want you to focus on all the terms, but I can just say is that our disturbed velocity is proportional to the drag divided by 4 pi u infinity times the vector of u infinity with two exponential terms expressed in the terminal velocity u infinity and the difference between the x component minus r. And then we divide the whole thing by r. And this is what we call an Oseen-led solution. So this assumes that, of course, the u infinity and the drag force are collinear, which is usually the case. Now, if you write in the Schiller-Neumann equation, so you can use any correction to that, but let's just go for a simple equation, we can say that our disturbed velocity equals 3 times the particle diameter times our Reynolds number correction divided by 8 times the Reynolds number times r to the power 3. And of course, that's a problem because it means that if we are looking at the center of the particle itself, so x equals xp, that we can't use this equation because we have a singularity. So to account for that, we can't get the disturbed velocity at the center of the particle, but we can make an average of the disturbed velocity by integrating it over a volume which is the same size as our computational cell. So that means our average disturbed velocity here is the integral of the disturbed velocity here over a sphere with the volume of h cubed. And if we now introduce the parameter alpha, and alpha is nothing more than 3 over 4 pi and the cubic root of that, we get an expression which for our averaged velocity equals pi times this alpha squared, which is just a constant, times dp hat times our Oseen correction times the u infinity, where dp hat is the particle diameter divided by the mesh spacing of our fluid resolution. And again, this is a complicated expression, and I don't want you to look at it too much. The only thing which is important to realize is that if we have Stokes limit, then this correction term goes to 1, and it will go to a slightly lesser value as the Reynolds number goes up. So the nice thing that it gives us a closed form of the self-induced velocity of a particle, which is pi times alpha squared times dp hat times u infinity, which is about 6/5 times dp hat times u infinity. So that's the maximum error you could get if you're doing a Lagrange particle tracking simulation. So let's try to do such a simulation and see what error we get. So let's put it to the test. So if we have a particle which is fixed in the domain and we have a flow going from left to right over our particle, we can write again our disturbance as the fluid particle minus u infinity, because u infinity is the undisturbed flow. And we can do a large range of particle sizes, mesh spacings, and particle Reynolds number. And if we now plot that, so here is the magnitude of our disturbed flow for a few hundred simulations. And here we have our dp hat. So this is the ratio of the particle size over the fluid mesh spacing. We can see indeed that this dotted line here, which is this pi alpha squared dp hat, is the maximum error that we can get in Lagrangian particle tracking. And if we multiply that with our Oseen correction form, so that complicated equation which you certainly don't need to understand or remember, almost all of the data collapses, so we can actually predict what is the error if we do standard two-way coupled Euler-Lagrange particle tracking. There's a slight or maybe a significant error in the estimation of the error for very high Reynolds number. So that's particle Reynolds number 500. But in most applications, that Reynolds number is very high because the particle Reynolds number is based on the slip between the fluid and the particle. So at very high particle Reynolds number, that starts to deviate, but up to Reynolds numbers of a few hundred, we have a pretty accurate estimate of what is the error in Lagrangian particle tracking. So we can also make a graphic tool. So this is basically a best practice guidelines tool. If you have a certain resolution of your simulation of particles dp, so this again is dp hat, which is the particle diameter over your mesh spacing. Here we have the particle Reynolds number. Then here we see ISO lines of the error, so ISO errors of your Lagrangian particle tracking simulation. So to give you two examples, if you take the mesh spacing of your Lagrangian particle tracking to be the same size as your particle diameter, at most Reynolds numbers, you're making an error of about 100%, which is significant. And that's already why in the literature we say, well, we have to go smaller. We have to have a particle to mesh spacing ratio of at least a factor 10. And very much to my surprise, if we do that, then even for Reynolds numbers up to 10, we have a mesh space, we have an error between 1 and 10%, which is significant. So with this tool, we are very confident that we can predict what type of errors you are making if you're doing a two-way coupled Lagrange particle tracking simulation. And this is exactly the reason why Euler-Lagrange particle tracking simulations of a fluidized bed are not very accurate, because at every particle you introduce a small error in your fluid phase. So far, this concludes actually part one of my talk. If we simulate gas-solid flows with the standard Euler-Lagrange method, we make an error because we estimate the undisturbed flow velocity from the actual resolved velocity field, which contains the disturbance of the particle. I've shown that this error depends on the particle Reynolds number and of the ratio of the particle size in the mesh spacing, this dp hat. And at low Reynolds numbers, we can say that that error is proportional to 6/5 dp over h, where dp is the particle diameter and h is the mesh spacing. I also showed you this more complicated equation, which actually maps the errors quite well up to particle Reynolds numbers of a few hundred. And even with the classical recommendation of the mesh spacing to be 10 times the particle diameter, you are still making errors of up to 10%, which is a very large error. So the second part of my talk is, can we get rid of the errors? And we've at least made a start of that. I hope I'll be able to convince you of that. So to go back to the equations that we need to solve if we want to understand what error we are making and how to circumvent it. Again, here we have our continuity equation. Here we have our momentum equation, so the standard Navier-Stokes equation, where we add this term m, which denotes the momentum exchange between the particles and the fluid. Here we have the Newton's second law to track each individual particle, our drag computation, added mass and history force, and we add this undisturbed force to it. And if we look at the standard source term regularization, so we're not talking about particle source and cell, but we're talking about a standard source term regularization. It's a k, which we convolute with the drag, added mass, and history. So the particle source and cell, which says we just take all the sources and we divide them over the computational cell. That's of course one way of fixing it, but you could also spread it out over any given volume, which is indicated by this convolution here. So in classical particle source and cell, we just divide it over the whole cell, all our forces. So what we do is actually that our k of r is just 1 over cell if it falls inside the cell. So you see it's a block here. And we get this error, which increases as our ratio of the particle diameter over the mesh spacing increases. Of course, we already know for 20 years that we are doing something wrong if we have to refine the mesh or we want to track large particles. So in a fluidized bed, we have a boundary layer, so we need to put some extra mesh shells, or we have a boundary layer in our channel. And I think the first paper to really address that formally was to use a volume filtered model. What they do for a volume filtered model, they replace this k with a spreading function. So you could say this is like a Gaussian kernel, which spreads the source terms of the particles over a region 2 delta, which can be proportional to the particle diameter or be bigger, so that it gets spread out over multiple fluid cells. And if you look at the error of that, it doesn't fix anything here. But if your particle becomes on the size of the mesh cell or larger, we can actually try to stop the error from becoming 100%. And this is implemented now in some advanced codes to do filtered models for the source term, so that they use a convolution. The question, of course, is we're not really satisfied with that. Can we bring down that whole line? Can we actually try to make our Euler-Lagrange model be as accurate as our fully resolved model? Because we know what the undisturbed velocity looks like. So again, for that, as we've done before in the particle source and cell model evaluation, looking at the error, we are again solving for low Reynolds number limit. So just for our disturbance velocity. So I won't repeat the derivation of that. And actually in the Stokes limit, we can use what we call the regularized Stokes limit, which is very well summarized in this paper by Cortez. And what we get is that we can indeed compute what is the effect of a particle on the fluid given a drag with a filter on it. So if we have a specific filter drag, what kind of disturbance do I get from the effect of the drag and the filter in one? And we have a fairly simple expression. Of course, I didn't put in Gn beta, which is a solution to the Poisson equation and the harmonic equation of our filter, which we've computed with the Wendland kernel. So typically people use Gaussian kernels to use in spreading functions with a length scale of sigma, which probably most of you are familiar with. These type of exponents are very difficult to integrate analytically in our case. So what we use is we use what we call a Wendland kernel, which is a polynomic approximation of our Gaussian, which we have a length scale of support radius delta, so which is the equivalent of the sigma in the Gaussian kernel. And the polynomial makes it much easier to go through the derivations of this expression. Again, the result is very complicated, and I don't want you to focus on that. But if we have our disturbance, we can write that as the drag force that we have divided by 120 times mu f times our delta. So that's our spreading distance of our kernel times pi times this r cubed. And because the highest order of r cubed is here, at the center of the particle point, we can directly say that the undisturbed velocity is the CFD simulation, so the disturbed velocity result, plus the drag force divided by 2 pi mu f delta, which is a surprisingly simple and effective equation. So it means that if I would do a CFD simulation with particles, I can interpolate the fluid velocity at the particle from the CFD simulation, so that would give me this velocity. I can add my correction term to it, which is this term here, which is very simple. And I have my undisturbed flow velocity, which I can then use to compute the drag. So that is a very simple and effective approach to that. Of course, I don't just need to know it at the center, because the disturbance of the particle is caused at a larger area than the center of the particle. So what I'm doing is I'm writing down an average of my disturbance at the particle P, which becomes the integral through space. So the average of the disturbance equals the average of my interpolated velocity with the particle there, plus this correction term here. Again, I don't want you to look at the complicated expressions. They're just there for completeness. If you're interested in that, please write me an email, and I'm happy to give you the details of the derivation. And indeed, what we get if we do the same experiment now, so we have a particle in a box and we vary the ratio of the particle diameter over the mesh spacing and over the error. The blue line is our corrected particle source and cell. If we do filtered the drag force, we get some better results for very large particles. But in fact, if we subtract the disturbance of the particle or add that to our interpolated value, we get the green line, and indeed we get a much more accurate solution for our Euler-Lagrange particle simulation. Again, it's still the worst if the particle size is the same as the mesh size, obviously. But it's much more accurate than even standard Euler-Lagrange for very small mesh spacing. So we've used the Stokes approximation. We can also go to a bit higher Reynolds number using the Olszyn approximation. So now we plug in the Olszyn approximation, which is again a correction of the Stokes approximation. And I'm not going to go through the derivation of that in detail. So now we have a recipe for recovering the undisturbed velocity in standard Euler-Lagrange simulation. So what we do is we do a CFD simulation. At each particle, we interpolate the fluid velocity. We add a correction to that. And what we get is the undisturbed fluid velocity in the range of the particle, which we can use to compute the forces on the individual particle. So let's test that out. So for a case setup, we're looking at a very simple case. It's a particle falling under gravity in a large box. So 200 times 200 times 200 particle diameters. It's a three-dimensional box. We vary the particle Reynolds numbers between 0.01 to 100, which is similar to what you get in a fluidized bed. We've looked at mesh space, particle diameter over mesh spacing from 0.1 to 5, so a large range of mesh spacings. And what we, of course, should get is if we have a particle falling under gravity, we should get the terminal velocity, which we can compute. And I'm going to call that UT. And if we have the particle diameter being only 1% of the mesh spacing, we get this dark blue line here. It indeed, the particle starts at velocity 0 and it accelerates to minus the terminal velocity. So it indeed falls and it goes to the correct terminal velocity. However, if I take the mesh spacing to be 1 or larger, you can see this orange and red lines. And in fact, the error that we get is more than 50%. So we cannot even predict the terminal velocity correct if you use a standard Euler-Lagrange particle tracking code for two-way coupling. If we now correct, as I've showed you, so we interpolate velocity, we correct that for the disturbance of that particle, and with that we compute the drag. Almost irrespective of mesh to particle spacing, we get correctly -1, so the ratio of the particle velocity over the terminal velocity which we expect. Of course, the biggest error of a few percent is when the particle diameter is the same as the mesh spacing. That is always going to be a problematic range, at least so far for particle simulations. If we go to higher Reynolds number, this starts to go down. So for very high Reynolds number, ironically, the Euler-Lagrange particle method is actually more accurate, but we're still making errors of over 50% at around particle Reynolds number 1. And with the correction, it's a little bit less good than at lower particle Reynolds number, but it's still much better than if we don't correct for it. And at a very high particle Reynolds number 100, we still see that the correction adds benefit to the particle simulation, although it's smaller than for the low-high Reynolds numbers. At the moment, we're also looking at the same fluidized bed case as I showed you previously. So it's a very small fluidized bed case, just 1.5 millimeters particle size, or that's very large for a fluidized bed. The thickness, a few particle diameters thick. We have 20,000 particles. And in fact, in this paper, which I wrote for my PhD, we show that standard Lagrangian particle tracking is not a very good tool to predict it. So we found, for instance, very large differences in even the dynamics of the fluidized bed because of this effect of this particle undisturbed fluid velocity. So what we get in the simulation, I'm just going to show you some snapshots. This is very recent work. We haven't analyzed it in detail, but you can see we can get a very high resolution of the fluid phase. So we can get a resolution which is close to a fully resolved particle simulation, but at a fraction of the cost. These are simulations which I can run on my desktop computer rather than having them run for weeks on a supercomputer, but gets results which are hopefully of a very similar accuracy. Here you can see the fluid flow velocity, and again you see features which are at the range of the individual particle diameters, even for a standard Euler-Lagrange particle tracking code. We haven't looked at very detailed, but for instance, if we look at the bed height, so we see here the slugging of the fluidized bed, we get very similar type of dynamics as with the bed. So over the coming months, this is a case which we'll look at in more detail and hopefully publish a final validation paper of the method. And with that, I come towards the end of the talk. So hopefully I realize that some of the derivations are a bit more complicated, and to be fair, they also took us weeks to do. So it's not that I want you to go along with that in a couple of minutes that I go over them. But there are two takeaway messages. The first one, if you do standard two-way coupled Euler-Lagrange particle simulations, the error that you're making is on the order of 6/5 times dp over h, where dp is the particle diameter and h is the mesh spacing. And to improve this, we have been working and will continue to work on what we call a volume-filtered Euler-Lagrange method. So basically, we spread out the force of the drag force over multiple cells. And with that, we estimate what is the velocity disturbance of a particle. We can subtract that from the recovered velocity. And with that undisturbed velocity, we can calculate the fluid forces. So not only drag, but we can also calculate the added mass and the history force with very accurate. What we've also shown is that the resulting approach converges with mesh refinement. So in computational fluid dynamics, mesh convergence is very important to show. Standard Euler-Lagrange methods do not show convergence with mesh refinement, but this newly method does. It also allows for all kinds of optimized mesh configurations. So if you have a stretch mesh or you want to resolve the boundary layer, you want to do adaptive mesh refinement, so a simulation which I showed where you refine a mesh as the fluid structures are evolving, because you automatically take into account the source term spreading and the reconstruction of the undisturbed flow velocity of that. At the moment, we're still working on wall-bounded flows because our spreading operator, as you've seen, is axisymmetric in a point. So if you have a wall of particle in a wall, of course, it's not axisymmetric because there's a wall. So we're also trying to look at what happens if we have non-axisymmetric, axisymmetric spreading kernels. What about particles with a very low Stokes number? And also looking at the very dense regime where we have particle collisions. That's also something which we need to analyze more carefully. Although even with the fluidized bed case, we already see a large improvement. And with that, I've come to the end of the talk. Again, thank you very much for the invitation. And I hope you at least understood the last two take-home messages. Thank you very much.
Okay, thank you very much, Berend, for a very interesting talk, and I think quite clearly explained how you are making next steps in developing these codes for modeling gas solid flows. Who would like to raise the first question? Any questions? Well, one aspect at least I wanted, Berend, and I guess with the paper you're working on right now, you're moving in that direction. The question is how these errors that you actually have in the velocities, how they translate, propagate into macroscopic properties of the bed, like for example the bed height that you were showing, and you can also think, of course, of bubble size and pressure drop, these kind of things. Can you say anything generic whether you expect that errors blow up or that they will average out and diminish when going from the small scale, the velocity per particle towards macroscopic properties, or is that hard to say anything about it?
No, I think you can actually say that these errors are bad for the motion of the individual particles, which you might not care so much about, but they're also bad for the macroscopic properties.
Mm-hmm.
Because for instance, your pressure drop over your fluidized bed, so the pressure drop here, will balance the forces on the particle. So if you look at the ergon equation, for instance, that's exactly what you do. You have a fluid pressure which encounters or counters the gravity force on the individual particles. So if you get your drag force 10% wrong, you're going to get a 10% error in your pressure drop over your total fluidized bed.
Okay, but you expect the error to stay of the same order of magnitude, not that it it blows up, or that things are averaging out at some point?
I think you're making similar errors at each individual particle. Yes, so it does accumulate. Yeah.
Okay, Chris has a question.
Yes, thank you, Ruud. Thank you, Berend, for a very interesting presentation. My question is a little bit related to Ruud's question. So you have done a very detailed analysis on errors for single particles in infinite fluids. And now I could imagine that in modeling a fluidized bed, you have other errors, maybe the non-spherical shape of particles or the interaction, the collisions between particles, where you make probably much more important errors than in the drag on a single particle. Could you comment on that?
Of course, in a fluidized bed, there are lots of things going on, and there are lots of approximations made. However, even if you want to get the dynamics and the pressure drop correct, you will need to know quite accurate what the drag force is on the fluid in each cell. So I would say that the errors you make in a standard Euler-Lagrange simulation of a fluidized bed, the ones that I discussed today, are more important than the typical shape or collision forces, even though, of course, they will present an error as well.
Okay, so but if I would ask a student to focus on the bottleneck in fluidized bed simulation, you would say it's not the shape of the particles, it's not the collisions, but it is the hydrodynamics of a single particle.
I think at the moment the collisions we understand fairly well, so we can have hard sphere and soft sphere models, and I think for spheres in a fluidized bed that's quite accurate. Obviously, if you're looking at a fluidized bed with straw particles, that becomes a very different story, because then the shape is so non-spherical that starts to dominate. But if you look at particles which are more or less spheres, then I think indeed the hydrodynamic approximation is the problem. Yeah.
Thank you.
Okay, then in the chat we have a question from one of our colleagues, Onno Kramer, who's working on liquid-solid fluidization. And he wonders whether you can apply the similar thing to liquid-solid fluidized beds as well, Berend.
So yes, I think you can. I focused today on the drag force. So we looked at the effect of the undisturbed velocity on the drag force. The difficulty, of course, if the fluid density and the particle density become in the same order of magnitude, is that you also get added mass forces, history forces, which also are driven by the undisturbed fluid velocity. So in principle, we could use or expand the framework that we're working on for also liquid solid fluidization. And in fact, I would say that the impact is much larger because the particle Reynolds number in a liquid solid fluidized bed is typically much lower because the slip velocity is smaller. So the short answer is the framework can be applied. It's not something that we have looked at yet.
Okay, but it will probably be more complex because of more forces being important in that case.
Indeed, you have added mass force and history force, which are probably of the same importance as the drag force in a liquid fluidized bed.
Okay, could you please remind us briefly what the history force is in a liquid solid system?
The history force is the fact that we have an accelerating boundary layer, which a particle goes through, and what that particle has experienced in its past still has an effect on the motion of that particle in the future. So the history force contains an integral of the relative accelerations over time, which is actually a very complicated force to approximate. There are a few approximations for it, but it's still a quite complicated force. Fortunately for gas solid fluidized beds, the force scales as the particle density over the fluid density, so it becomes small for gas particle flows. But as the fluid density increases and comes near particle density, that force becomes important.
Okay, thanks.
It's also called the Bassett force. Maybe that's.
Yeah, okay, that's indeed a term we also often use. Yeah.
Yeah.
Any other questions? Was everything? clear. Yes, somebody already asked. The lecture is being recorded, and it will be posted on the website later. So Laura can provide us the link, I think.
I'm also happy to give you a copy of the slides. I can email it to you. So if
that would be very helpful as well, Berend. Great. Yeah.
Definitely.
No further questions?
I have a small one.
So go ahead. Yeah.
Yes, I see the arrow at the end is proportional to the mesh size, basically. So how many particles you can account for in one cell. But the other way is if you have more particles, large mesh, but then you lost the local dynamics of your fluid. Do you have any comments on?
Well, that's exactly the problem. So there are two competing things. So you would like to have a fine fluid mesh to be able to capture the structures and details of your fluid. But up to now, there's a limit on how fine you can make that mesh, which is always said to be about 10 particle diameter. So you can't go finer. And that's always been the trade-off between doing Euler-Lagrange simulations. And I mean, our holy grail is that this Euler-Lagrange particle simulation methods are starting to approximate the accuracy of fully resolved without having to pay the cost for fully resolved.
Yeah, I see. So if we don't apply these corrections, so we can stick to a 5 to 10 this ratio, right?
Well, and to my surprise, because I've been telling people many years in the best practice guideline series courses that we give, you could do a factor 10 and then the error is very small. You can still get errors up to 10% in drag. So that's still a significant error if you take factor 10. But that's in literature always been taken to be a safe guideline, you could say, yes.
Okay, thank you.
You're welcome.
Okay. Any final question? If not, then thank you very much again, Berend, for a great talk. We really appreciate the time you spent on explaining about your research.
No, thank you for having me. Really a pleasure.
Okay.